Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Started a few minutes past. So it's my great pleasure to introduce Svetlana Volkova. Svetlana is from Johns Hopkins University, interviewing here for a postdoc position.
Thank you so much, Hiram, and thanks for having me. And today we'll be talking about social media predictive analytics methods and applications. I don't think I need to sell you on the importance of social media nowadays. Social media gives us access to personalized, timely, diverse, multilingual data on such a large scale. You can think we are talking about millions of messages and billions of users, and this kind of data allows researchers to build a variety of social media predictive analytics. As soon as researchers started mining this data, media picked up, and you could see headlines like Facebook data know you better than your mother, or computers judge personality better than your friends, or even scary ones like your social media profile can cost you a job. And a really controversial study that was done by Facebook this summer, where researchers manipulated user emotions to study the emotion contagion in social media. So people who are working this kinds of research have to be really careful about ethics and privacy. Let me tell you about my research. I use natural language processing and machine learning to work with social media. I'm primarily focused on author attribute prediction. I also do emotion and sentiment classification, and a bit of attitudes towards events and entities. You can think about an example of Russia and Ukrainian crisis, for example. This research ended in a variety of publications. I have also been working on unsupervised dialogue learning, language grounding, and information extraction and named entity recognition in the medical domain. So let me tell you why language in social media is so interesting. First of all, it's very short. It's only 140 characters. It's very lexically divergent and abbreviated and multilingual. We have many, many languages, and actually more than 80% of Twitter is in languages other than English. So you can mine tons of languages easily. But doing this research is very challenging. First, we are working in a highly dimensional feature space. And also another issue is a data drift. So for example, one concept that was popular a year ago, like Euromaidan in Ukraine, is not discussed anymore. Another issue is user activeness. And since users are active in social media to a different degree, it reduces the generalization of the models. The next issue is topical sparsity. People don't really talk about politics in their everyday messages. People who are politically active, they are talking about politics, but random Twitter users, they don't care about politics. The same is the relationships and so on. And the last but not the least is dynamic and streaming nature. We have to work on the models that allow to take into account evidence that is coming over time iteratively, and that's what I'm going to talk about today. So here's the outline of my talk. I will start with machine learning and NLP for computational social science and tell you about our study relating user properties and emotions on Twitter. And then I will move to machine learning methods, and we'll talk about online streaming inference, as well as dynamic learning and inference from the mixed streams. So users in social media are connected. You have your friends, you have people you retweet, you follow, you mention. Imagine we have predicted user emotions, so things that they feel and things that they feel, their opinions, And also we have demographics for these users, predicted or ground truth. So we want to study two questions. First, whether we want to figure out whether there are emotional differences between users and their neighbors. And second, we would like to, if there are such differences, we would like to correlate these differences with user demographics. And this study was inspired by this controversial research on emotion contagion on Facebook. So let me tell you how we sample the data. And sampling is really important when you work with social media because there are so many sampling biases you can bring while working on social media. So for this specific study, we sampled English-speaking Twitter users from the US and Canada, and we were looking specifically for average Twitter users. We didn't want any celebrities or we didn't want empty accounts. We sampled people who tweet between 4 and 10 times a day and have more than 20 friends, and it's not a random number. This was empirically estimated on a different data set and confirmed in the literature to get random Twitter users, average Twitter users. So following this, we got 10,000 random users with their 200 most recent tweets. After that, we used the same strategy to sample their neighbors. We sampled 5 friends on average of people they mention and 5 of people they retweet. At the end, we ended up with having 100,023 users, 25 million of their messages. This is the size of the data set we are working with, and it's comparable to this emotion contagion study on Facebook. It's huge. So let's talk about the approach. First, we would like to be able to predict user attributes, user demographics. To do that, we have developed supervised models, and to get labeled data, we used crowdsourcing. Then we use this annotated data to perform attribute classification. The next, we developed emotion. We used data annotated with emotions. And actually, to annotate this data, we use distance supervision. And by distance supervision, I mean that here is the example of the tweet that includes the hashtag sadness. And we say that this is a sad tweet. Of course, this is not perfect, but this is the best we can do as of today. As for sentiment, we used publicly available sentiment data sets, collected tweets labeled as positive, negative, and neutral. Using this label data, we developed emotion and sentiment classification models and applied emotion and sentiment classification models as well as attribute classification models to make predictions for a range of users and their tweets. So imagine you have a database where you have users labeled with their demographics and you have tweets labeled with emotions and sentiments. Yes?
Crowdsourcing?
Next slide. Really good question. So now let me tell you first, how did I get the annotations? And second, how did I build these classifiers? So how do we get this label data? It's really challenging because we are coming to a new domain and we are doing supervised classification. We need to get annotations. It's really costly and difficult, time-consuming to get. There are several ways you can get the ground truth. First, you can think about fun psychological tests that people take voluntarily on Facebook. They have nothing to do. They just take these tests, and researchers are collecting this data. And I think it's really clever. Next way you can collect this data, you can go and look for self-reports. You can look for tweets that say, I'm a Republican, or happy X birthday to me. But this kind of approximation will bring a lot of biases to your data collection. The next possible approach will be information. So for example, like Tor with people from the Cambridge, for Facebook include information like gender, age, relationship status. But unfortunately for Twitter, there are no such data, and it's extremely sparse. Another approach, you can use distance supervision, or alternatively, you can go and do crowdsourcing. And actually, crowdsourcing have been successfully used for a variety of natural language processing tasks that are more challenging than author attribute prediction. For example, machine translation or predicate argument agreement, really difficult, challenging tasks that require a lot of intelligence. And to mention that all of these data annotation approaches have a lot of biases. If you want me to tell more, we can talk about it later. So how did we do the annotation? We decided to go with crowdsourcing. We used the trusted crowd on Mechanical Turk. We paid $6 an hour. And in addition to that, we also embedded a lot of quality control questions to ensure the quality of the annotations. We showed 5,000 profiles to these users, and we asked annotators to label a variety of attributes for us. And on this graph, I'm showing you the inter-annotator agreement, which we estimated on a random sample, on a random 2% sample of the data. Due to budget constraints, we only annotated 5,000 profiles by one annotator, and we calculated the inter-annotator agreement on a sample of it. So as you can see, some of the attributes are highly agreed on, like ethnicity and gender. The agreement is really high, and then for the majority of the attributes like children age, life satisfaction, income, optimism level, the agreement is solid, but for some attributes like political preferences, religion, intelligence, the agreement is fair. So you should think about it that these attributes are really difficult to predict. When annotators are looking into this data, it's really difficult for them to find the signal in the profile. Did this slide answer your question?
Right, so it's the answer is it's a subjective thing from crowdsourcing.
Exactly, and I will mention this issue later, yes. So we are looking for subjective perceived annotations, yes. So, yes.
So, did you let people express any sort of uncertainty or kind of confidence in their labeling?
Not in this crowdsourcing experiment, but I did it for a variety of the annotations for my thesis. Actually, I don't think it helps to expressing the confidence. If I just say, first of all, we didn't collect binary annotations, we collected multi-class annotations. So you can think about it that we gave them a freedom to express the degree of confidence on the scale. So for example, for narcissism, we say, do you agree that this guy is narcissistic? And we say, strongly agree, neither agree or disagree, agree, and agree strongly. Like on a scale of 5, for example, for this specific attribute.
Was that true for like male as well? So
No, for male, it was binary. For binary attributes, it's binary. So now yes?
Can you tell us what this measure is on what's Cohen's kappa and what does 0.4 of Cohen's kappa mean?
So it measures how annotators agree on their annotations. Usually, you don't collect one annotation, you collect more than one, and then you see how often they agreed on this measure, on the annotation.
So the income is discretized into some number of bins.
Yes,
and then
exactly.
How often do
Yes.
they agree?
Yeah. Yes?
It adjusts for chance agreement, is that right?
Yes.
Okay, so we see essentially how much more they agree than would be expected by chance.
Exactly.
Okay.
Yes. It's a standard measure for these kinds of tasks. So now let me tell you, how did we actually build the models? We are doing nothing fancy here. We are working with log linear models or logistic regression, and we are binarizing all of the attributes. So you can think about it as a binary classifier, and we are working with a range of features. So you can think about word engrams, character engrams, or stems, co-stems, linguistic features. You can also think about sociolinguistic, syntactic, and stylistic features like part-of-speech tags, punctuation, parsed trees, different lexicons. Another kind of feature is affect, like emotions, sentiments, attitudes, topics, communication behavior, and network structure features. But in this work, we have only used the top 3. But if you're interested in talking more about these features, I can tell you more. So back to the question about the subjectivity. Here we are trying to perform a more ethical study compared to what Facebook did, but the study has several limitations. First, we are working with subjective annotations. These are perceived annotations. And some attributes are more difficult to predict than others and to annotate, like income. It's really subjective. Intelligence is really subjective. Also, we are using distance supervision to collect this emotion annotations. And when we use it, we are not really taking into account the irony. So for example, imagine there is a tweet where you say, it's Monday, #joy versus it's Friday, #joy. So the hashtag was used in a sarcastic, ironic way, and we are not actually taking it into account. Moreover, we don't have any no emotion class, which is again biases our results a bit. So yes, Chris?
If they work at Microsoft Research, then #joy on Monday would be very appropriate.
Of course, yes. How to interpret our results correctly? Let me warn you that we are drawing conclusions from predicted attributes, not ground truth. And also, we don't imply any causalities. We are only looking for correlations. So here are the results for attribute classification, and I'm showing you the area under the curve because the data sets were imbalanced for the attributes. And as you can see, race and gender are easier to predict than, for example, religion. And like education, intelligence is not bad. And actually, these numbers are really good. They beat the state of the art. And my models from my thesis were the state of the art in this field. And we are actually beating these models. And the evaluations were done using tenfold cross-validation. Next, let me tell you how did we do in terms of emotion and sentiment classification. So in addition to using bag-of-word features as we did for attributes, we added stylistic and syntactic features like negation. For sentiments, it's extremely important to distinguish the feature not happy versus happy. We also add elongations, capitalization, hashtags, emoticon, mixed punctuation, and you wouldn't believe, but these features significantly improve your F measure. So regarding F measure, remember we are doing 6-way classification into 6 basic Ekman's emotions, which is joy, sadness, fear, surprise, disgust, and anger. And we are getting really good F measure, which is now the state of the art, and we are beating a variety of previous work on that. And I can even tell you why we do that. First, we have much more data. As second, we have much better features. Nothing fancy, but it works. Regarding sentiment classification, we are classifying tweets into 3 classes, positive, negative, and neutral. And again, we are getting a really good F measure, which was actually estimated on a standard test, benchmark test for these kinds of tasks. And actually, the first team got 69% F measure, and we are getting 66. It's not really fair to compare because we were using different training data, but for the purposes of this study, give you an idea how well we do in terms of classification, that's the way to compare. So let me recap a bit on the task. So what we are trying to do, we are trying to measure the emotional differences between users and their friends, for example. And imagine you have a Twitter user for whom you have a variety of predicted attributes, and you have a set of incoming tweets per user. For every incoming tweet, you predict emotion and sentiment, and we call it the environment emotional tone. And then you have a set of outgoing tweets per user, and for every outgoing tweet, you predict emotion and sentiment, and we call it the user emotional tone. And we are looking for deltas. We are looking for differences between these distributions given demographics. So given that this guy is a male, how these 2 distributions are different. So let me tell you about the methodology. First, we would like to measure the similarities between 2 distributions. And we do this using Jason-Shannon divergence, which is a symmetric KL divergence. So basically, we are looking we are comparing the incoming distribution of emotions and outgoing distribution of emotions for each user. And then the next thing we do, we look for these deltas. So imagine we take one emotion, for example, sadness, and then we say, what is the proportion of your outgoing sadness minus your incoming sadness normalized by the sum? And we do this for every emotion, and for every user, we have these delta numbers. And then, really simple, to compare these distributions of deltas, we perform a Mann-Whitney non-parametric test on Jensen-Shannon divergences and emotion differences. So for example, let's take people who are predicted to be male, and let's take people who are predicted to be female, and have a distribution of sadness in the male group and the distribution of sadness in the female group. What we would like to compare, we would like to compare two means of these distributions and say whether these means are statistically significantly different. So that's what we do for the analysis. Any questions here? Okay, so let me show you the results. So we found that the majority of, half of the emotions actually were amplified. And let me tell you what I mean by amplification. So if the amount of sadness that I'm outputting is more than the amount of sadness that is incoming, it means I'm amplifying sadness. Vice versa, if the amount of joy or if the amount of sadness again is lower than the amount of incoming sadness, it means I am dampening sadness. That's the way we use these terms of amplification and dampening. So for these three emotions, for disgust, sadness, and joy, they are always amplified to a different level by users with contrastive demographics. Except people who are older and have kids, they always dampening sadness, which is very interesting. And actually, in the psychological literature, we find similar trends regarding age and having kids. The same is for joy. All of the groups of people with predicted demographics always amplifying joy. However, people who are predicted to be stressed and pessimists, they are dampening joy, always. For the next three emotions, people are dampening surprise, fear, and anger, except for people who are predicted to be dissatisfied with life and not excited. People who are dissatisfied with life and not excited, they are amplifying, they're actually amplifying anger. Again, you can think about it as stereotypes, but that's what we are getting from the data. And it's confirmed in the literature, and given the scale of the data, I think these discoveries are really interesting. And then we found really nice things that haven't been reported in the literature, but it's very interesting. First, regarding sentiment, let's talk about neutral sentiment. All of the people amplify neutral sentiment, so they say more neutral things that they get, except people who are older with higher income and degree. You can think about it like that. People who are older get more money and more educated, they are more opinionated. They express more opinions, positive or negative. It's like in the reviewing process. You don't say the number in the middle. You either don't like the paper or you like the paper. So I think people are just more confident by having money and being more smart. Regarding positive and neutral sentiment, it's always dampened, except for male users and people who have kids. Male users and people with kids, they are amplifying positive sentiment. They are more positive compared to the contrastive attributes. Okay, so given these results, we decided, first, we found these correlations. They are really interesting. Let's use these correlations. And what we decided to do is to build better features for our models. In addition to using bag of words features, we decided to go with sentiments and emotions, and that's what we got. So I'm showing you a similar graph that I showed you before for the variety of attributes. This is again the area under the ROC curve, but I am adding outgoing emotions and sentiments as features, and the emotion and sentiment differences. And you can see that you can compare in the column on the right how and what delta gain we get for every attribute. For some attributes like gender and ethnicity, the deltas are lower because we did good job before in predicting these attributes. But for some attributes like, for example, political preference and age, we are getting 17-point improvement, which is really good. Also, to mention, you can think about emotion and sentiment features as a meaningful dimensions to reduce your feature space, because these emotions and sentiments were predicted from the tweets, from language, and you can think about it as basically as a dimensionality reduction technique. But if you use SVD, you don't know the dimensions. Here, you give the meaning to these dimensions. So to summarize, first, we showed that different demographics leads to varied reactions in the emotional between users and their neighbors. Given that I am a female, I will react differently to anger tweets compared to a male user. And also, when we use emotion, sentiments, and this delta as features, we are significantly improving author attribute classification, which is really important. But let's ask what if, and let's think about the real world scenario. In the real world scenario, you have tweets that are coming over time. You don't have you don't have a setup where you have a set of training data and a set of test data like we used before. In the real world scenario, you will also want to take into account the relations between the users. So far, we predicted users independently. We didn't look into these users as connected in the social network. So right now, I want to switch to the machine learning methods and tell you more about streaming inference, how to make predictions on the fly in a streaming fashion. And then in addition to that, I want to tell you about the learning and predictions. So we want to learn and predict on the fly. So unlike previous approaches, which use static batch predictions, which means that we had offline training and offline predictions, and we didn't really take into account network structure, we would like to move to streaming online inference, which means that we will still have offline training, but we will try to make predictions online. In addition to that, we would like to explore 6 different kinds of relationships between Twitter users, like friends, followers, retweets, and so on. Going beyond that, we would like to learn over time as well as make predictions over time, which still means that we are making online predictions and relying on neighbors. But in addition to that, we use iterative retraining, we use active learning, and we also do some effective rational annotation, and I will tell you what are these rationals. Adding these advancements to our approaches will help us to handle the dynamic and streaming nature of social media. We will also explore the network structure by making predictions from joint user-neighbor streams. And also, we will look more into the trade-off between prediction time and model quality, which is really important for practical applications. So let me start with iterative Bayesian predictions. So we have a task. We want to predict user political preference. And to make these predictions, we are using simple Bayesian rule update, where we start with some prior, and the issue of priors on Twitter is extremely important. And if you want, I can talk more about it. So we start with some priors, and every time we get a tweet, we update our likelihood. So we're getting the probability of the tweet given the class, given a Republican, and every time we update our posterior belief about the label for this specific user. Let me show you an example. So at time t0, we only know the prior. Let's say we start with a balanced prior 0.5. It's a binary classification task. As soon as we get a tweet per user, we update our posterior. And then we get a tweet from user neighbor, we update our posterior. A tweet from the user, we update from the neighbor, and so on. And this posterior is actually telling you our confidence in the prediction. So you can think about it as at time tau 2, I am 62% confident that this user is a Republican, and at time tau k, I'm 77% confident that this user is a Republican. So more tweets you get, you improve your posterior belief, and actually you, the developer, you can think about this when you should stop, and I will tell more about the strategy when to stop. So whether you want to have less confident predictions versus more confident predictions, you decide when to stop. Now let's move to learning. How do we predict this over streaming data as well as learn better models? Again, we are doing political preference prediction. We have a small set of users labeled as Democrats and Republicans, and we have a bunch of unlabeled data. So the simplest brute force approach will be, as soon as we get new tweets, we train the model, we train the log linear model, we predict for the unlabeled users. You get more tweets, you re-estimate your weights, you use it again. You get more tweets, and again, you apply it in the streaming fashion I just described you before. So this is a simple scenario, just retraining your model. It requires a lot of computations. Again, your feature space is really, it's extremely sparse and it's highly dimensional. But you can use this iterative batch retraining in two scenarios, with and without rational filtering. And rational filtering, it's a totally NLP concept. So in addition to asking people to annotate users as Democrats and Republicans, we actually asked them, why did they make this decision? And they highlighted n-grams in the tweets that are predictive of Democrats versus Republicans. So for example, a unigram like voters, president, passes, senators are predictive of users that are Democrats. And economics, Palin, drilling, representatives, Wall Street Journal, Hunt, actually T-SOT, are predictive n-grams for Republicans. And when I say we apply rational filtering, which it means that when we retrain the model, in addition, instead of adding all of the tweets that are available up to this time, we only add tweets that include these rationals. Doing this allows us to shift the classifier to make more accurate decisions. So your training data is extremely accurate. It's really precise. And it's lower dimensional, so it requires less computation, and it actually gives you better predictions, better quality of your predictions. So now let's move to active learning. In the active learning scenario, similar to iterative batch retraining, we have a set of labeled users and a set of unlabeled users connected in a network. And again, we are using the same Bayesian rule update when we make predictions. As soon as we predicted a label for a user, and we are confident in this prediction, and you can think about confidence, you decide about this confidence, whether it's high, low, you can play with this threshold, 55, 75, 95% confidence in this user being a Republican. As soon as we classify this user, we can add it to the labeled set. We can also ask mechanical Turkers to highlight the rationals and to confirm the label. And then we retrain the model, apply to the rest of the unlabeled users, again, update your posterior for the rest of the users, and so on. As soon as you classified more users and you're confident in your classifications, you add these users to the label set, ask annotators to confirm if you want, retrain the model, apply it again, and so on. Update your posterior, and so on, until you classify all of the users. And in the active learning setup, you also can think about rational annotation approach. You can also think about classifying without the oracle. And by oracle, I mean that if your mechanical Turkers always give you the correct decision, they are 100% correct all of the time. You can do it using the majority vote. You can ask many Turkers to do that. You can ask 5 labels for 5 people to label the same user. But again, it's a trade-off in time and cost and the quality of your predictions. Using this streaming online approaches, you should think about optimizing for targeted advertising, for example. And it's really interesting. And we have a description about this experiment in our recent AAAI paper. But let me just summarize it for you. So you might want to optimize toward your prediction quality. You might want to have models that are accurate always over time. And they should be accurate today, tomorrow, the day after tomorrow, always. So in order to do this, you would like to use models with rational filtering. So really, really precise models. And you want to higher your confidence threshold. So basically, you will always say, I will only take people whom I'm 95% confident that they are Democrats or Republicans. On the other hand, if you want to deliver your ads faster in time, so you want to have correctly classified users faster, tomorrow, not in 1 month. You would rather use models that don't use rationals. They give you higher recall, and you use lower confidence. For example, 55%. So you allow for some misclassifications, but you want to deliver ads faster. And finally, data selection. We run a bunch of experiments when we only take a user stream from only user tweets versus user neighbor tweets, and we combine it with different neighbors, and there are different strategies. You can select your neighbors. We found that always it's better to get predictions from the user neighbor stream. Neighbors tell many things about you. And even if you don't have any tweets, your neighbors can predict your attributes. So joint streams are better. To summarize, our results show that online learning is much better than batch predictions, and it's actually really suitable for this kind of predictive analytics in social media. Active learning is better than iterative batch predictions in terms of quality of the predictions. And your neighbors completely give you away, so always use mixed streams. It's not noise, it's actual signal that is coming. And finally, rationals significantly improve your classification performance. So go into more linguistic features when you do this kind of text analytics. To recap, let me tell you why my models are good. So this approaches actually model streaming nature of social media, which people just started doing, and I think it's really important instead of just using train and test and build classifiers. Next, our models allow to make predictions for the users for whom you have limited content. For example, I don't tweet, and even I don't tweet, you can say many things about me. And actually, different kinds of neighbors make different predictions for like gender, age versus political preference. For example, people whom I retweet and mention can tell political preference better than the rest of the neighbors. People whom I follow are predictive of my age, and people whom I'm friends with, people who are really close to me, I'm friends with Yoram, Yoram is friends with me. These people are predictive of my gender. So different neighbors are predictive of different attributes. It's called attribute assortativity. And it's actually really interesting and to see that we can get the signal from the data. Also, we actively learn from crowdsourced rationals. And this kind of active learning allows us to account for the data drift. And the same is this one is topical sparsity. So since we are making predictions from multiple streams instead of just a user stream, we are also considering friend tweets, follower tweets, user mentioned tweets. We allow for this topical sparsity, which means that I rarely talk about politics, but my friend Yoram talks about politics, or Sophia talks about politics more. And if I'm getting tweets from these people, and there are some strategy how to do this. It's called exploration versus exploitation, and we have some actual experiments on that. It's better to explore your neighbors. It's better to get one tweet from each of you rather than getting all tweets from Yoram, for example. Which is, again, really interesting, and it helps to solve the issue of topical sparsity. The next is learning on the fly. We learn on the fly, we change the dimensions of our feature space, which allows us to take into account this data drift. If there is a new concept that will appear tomorrow, I will be able to pick up this concept because I am learning new models and I am extending my vocabulary while I'm making predictions. And finally, we build a really flexible framework which allows you to add more features easily. You can think about word embeddings, which is really hot right now, and it's really helpful actually. You can think about interests, profile information, tweeting behavior, and so on. We can add it easily. With that said, I would like to thank all of my collaborators. I'm really grateful to them, and thank you for having me, and I'm ready to take questions. Questions? Katya.
I was curious about the active learning strategy you developed. I didn't quite understand how you select tweets that you want to be labeled. Could you say a bit more about that?
You can apply different strategies. First, you can think about the threshold. So if you say, for example, there are a bunch of people, I'm 70%, more than 70% confident in their predictions. You can randomly sample. You can use any different strategy, like you can ask, you can get the majority voting from the annotators. There are standard active learning, like there are standard ways you can select next examples to annotate in the active learning setup. What we did in these experiments, we actually just took randomly from the people with the highest confidence. You can also think about taking people with the lowest confidence. So if you want to make predictions of, if it's a really difficult example and you haven't been able to classify this user over like 10 tweets, and it's very difficult, you can think about getting users with the lowest confidence instead to get labels for them.
Did you compare different strategies? Or it seems like the
Not yet. Yes, but it's a very nice question. Yeah, it's really interesting to explore. The next step. Yes.
Can you go back to this first experiment where you were talking about, you had your arrows about amplifying?
Yeah, sure. Yep.
Right. So I'm trying to understand what went into these. So when you have something like stressed pessimists seem to dampen joy, is that the correct interpretation there? But is it the case that you're predicting whether people are stressed or pessimists based on the same tweet data that you're using to measure?
Very good question. Of course, when we asked for annotations and when people labeled a completely separate data set, which is not relevant to the data set we are analyzing, people might, in their head, they make inference and they think, okay, this is like this person is expressing a lot of joy, it should be an optimist, right? So of course, I agree that there are some embedded correlations between emotions and sentiment that were used while people made inference during their annotation process. But since we are using a completely different data set, we are just picking up the signal that was present before, that was in the data, we learned from this data, and we are making predictions for the test set. So I don't think it's an issue because we are using a completely different data set to train and test.
So for a user in the test set, you're taking the same tweets are used to predict the stress pessimist and the amplification of joy.
Yes. Yes, but that's the assumption you always make. You think your words are independent. They are IAD when you make predictions, right? Or your features are independent, which is not always true.
Yeah, but I mean, I think it's maybe a similar question to what Danny said. If you can think of, one definition of a pessimist is somebody that looks at their environment, whatever their friends are saying, and they only retweet messages if they're sad. So, it could be the case that people that are doing this task of mechanical theory ask them, is this a pessimist?
But that's what they make in their head, right?
They could be looking at all, the friends of this person, seeing what they tweet, looking at that person. It is, it's a matter of interpretation. They could be doing that. I don't think it's possible to rule this out.
Of course, since we showed them all of the information in the profile, they might click into the link, they might follow followers and check if they do really thorough work while annotating. So as I said, there are some bias, but I think your question is different. It's more like the features you use for attributes are similar than the features you use for emotions. Yes, but. Yes and no, because the feature vector you build for the attribute prediction is a user-based. So you aggregate all tweets per user it's less sparse, and it's the dimension is the size of your vocabulary. But for tweet-based predictions, you have a completely different vocabulary, and the features are really sparse. It's done on the tweet level, so these are the difference. So I don't think the feature. I truly think that the predictions are independent in this scenario. Did you see what I mean?
Well,
Let me tell you one more.
Is there evidence to support that? I mean, like, so I guess I still don't see how it's ruled out that, some people just have more pessimistic tweeting behavior, and so they're classified as pessimists, and they're classified as dampening joy.
They are not classified as dampening joy. We found that they are dampening joy based on their tweets, based on their emotion predictions. That we are not classifying these people as dampening tweets, as dampening emotions. Let me start again. So when we train our attribute classifiers, we have a vocabulary, over 5,000 profiles annotated with attributes. This is the vocabulary of size X. And we build a feature, every time we get a new test instance, we just build a feature vector over this vocabulary. Let's take binary features, word features, right? Of size X. For each user, we are trying to make a prediction of income, for example, or like you want pessimist. We want to label this user as a pessimist or optimist. When we are predicting emotions, we are training different classifiers. These classifiers are tweet level. So we have 75,000 tweets labeled with emotions, completely different vocabulary of size Y. And every tweet we get from the user, from the users, we convert to this feature vector, which is really sparse because it's on the tweet level of size Y. So for attribute predictions, we worked with feature vectors of size X. For emotion predictions, we worked with feature vectors of size Y. Different. And I think that's why these two predictions are independent, even given the fact that they are predicted from the same data.
Explain the amplified dampen, then that is a comparison between me and my neighbors?
Yes.
So can you
Sure.
define well the...
So amplify, simple example, let's take sadness. I'm getting 60% sadness from my friends, and I'm outputting 30% sadness. Am I dampening or amplifying? I'm dampening sadness,
So that
right?
would be you're labeling the tweets I get
Yes.
for sadness. Define the ratio of those tweets that are labeled as sad, predicted as sad.
Let me show you this example again. Quickly. You should ask me before. So you have a user. For this user, you have a set of tweets that are incoming, right? For every tweet, you have a sentiment and emotion label. The feature vector is of the size Y. On the tweet level, tweet-based prediction, we label every tweet as sad, fear, disgust, and so on. For this user, you have a set of outgoing emotions and sentiments, outgoing tweets. We label it with emotions and sentiments, and we look for normalized deltas. So for every emotion, you get 60% sadness incoming, 30% sadness outgoing. The difference is 0.3. And I say, let's take all female in my data, and let's take all males in my data, and see whether the mean proportion of sadness and the mean for female users and the mean proportion of sadness for male users is different, and whether this means are statistically significantly different. And that's what I do. And when I say dampening, it means that all of the female, like the average estimator for the female group is dampening versus the average mean for the male group. That's what I meant. Yes?
I also like to ask you a question. You were talking about data drift. You're saying, okay, there are some things that are topical in the data, and the way you got around that, in one of your papers was you use people to annotate, say, Republicans versus Democrats. People read the news all the time. They know, if they're talking about the candidate, they know whether it's a Republican or a Democrat candidate. So basically, you use people's judgment.
Yes.
You plug people into the system.
Yes.
To solve some of the problem. And I
Yes.
was just wondering whether there was a way of automating this. So I'm thinking specifically Republicans and Democrats. You know, if you search through Wikipedia, you would know who the Republican and who the Democrat candidates are.
Yeah.
So maybe one way of replacing people throughout this process, which are very expensive, is using some automated tools or some knowledge reasoning. Do you think that's doable?
Totally doable, and I actually did it for one of my papers. But it implies several biases when you do it like that. So in one of my papers, we used distance supervision labeling strategy, where we say people who follow Obama and Biden during 2012 election process are bad, don't follow Romney and Ryan, are Democrats. And people who follow these two guys but don't follow Obama and Biden are Republicans. But using this strategy brought a lot of biases in the data. We actually sampled users who are really politically active. Since they are following these candidates, they are talking about politics really, really a lot. And when we tried to generalize these models to a random sample of Twitter users, these models don't really generalize, unfortunately. That's why I told you that every time you try to do analysis in this kind of, on this kind of data, and sampling is extremely important. The way you annotate this data is extremely important. And unfortunately, people don't share the data they collect in social media. That's why I couldn't do any comparison with the existing work. I actually have some numbers. I can show you where we stand in terms of annotation, but it's not the fair comparison. Just one sec. Because the data is different, so the training and test data is different. Yeah, so where do we stand? This is the slide. Yeah. So, first of all, in this work, we worked with a variety of previously unexplored attributes. People have been primarily working with gender, age, and political preference on Twitter. And here are the results for all of the existing models. So far, like my models were the best, but the models we built with URM actually outperformed the state of the art. Again, I can't make a direct comparison except with testing or training on MSR data and testing on my data, because I have my data, right? And actually, when I do this, and it was Katya's question before, when I do this, we are getting higher or comparable performance. But I can't compare with this people or this person or that person. So, yes?
There is that Cohens kappa as well. What is accuracy there?
This is the accuracy I'm showing. This is the prediction accuracy. If we want to predict user as male or female, this is the accuracy these people get, different data set. And this
doesn't include it includes chance as well.
No,
Is it a measure of skill?
No, I'm not taking. The thing is that all of the previous data sets were balanced. It's 50-50, so the prior distribution is 50-50. Actually, here I'm showing you the raw curve. Actually, it's not accuracy. So it's not fair to compare, but it gives you an idea where we stand.
But I mean, on this slide, you're talking about, so you take your machine learning algorithm, you run the tenfold cross-validation.
Yes, exactly.
And you look at the ground truths that you have, what proportion
perceived
of the
ground
cases
truths,
yeah. What proportion of the case it was right. When you're talking about inter-rater agreement, you're not running any machine learning algorithm. No. You're just looking at what other people said, and you measure how many cases they agree, roughly.
Yes.
Okay.
Yes, exactly. And ROC is basically taking like two random people, like one male and one female, and labeling them correctly.
Do you have a sense of, coming back to that question, do you have a sense of where your algorithms would stand in comparison to this inter-annotator agreement? Have you essentially reached the accuracy of what could be found in the data? Are you close? Are you far away from that?
This is a really interesting question, which gets back to a new paper at PNAS, where researchers found that actually machine learning models are better predictors of user personality than annotators on Mechanical Turk.
How can that be?
It's a really challenging task.
Well, I guess it's doesn't know them, or I mean, you can compare versus the person self-reports or their personality that comes out of a questionnaire, and their family sometimes doesn't know them.
You don't
That's
believe
not a
that
surprise,
computers
right?
can do better job? You don't believe in
No,
this?
I mean, if you get your labels from crowdsourcing, then how could you? What would?
Oh no, that's not my work. That's the other people discovered with their personality data. They collected labels completely differently. But
So we know that crowdsourcers make a lot of mistakes.
Yes.
How does that affect the models that you train and the results that you're observing?
say your question again, the last bit again.
So we know that crowdsourcers make a lot of mistakes
Yes.
and they have biases. So how does that affect the results that you're getting here?
I know that they make mistakes, but I think on a large scale, since we collected 5,000 profiles, it's a lot. I'm hoping that this noise will disappear, and my models will still. Of course, I agree. Because when we wanted to make these annotations, we had to decide whether we got 2,000 profiles annotated by 3 people or 5,000 by 1 person. We have 1 budget. And we decided to go large, to go big, and get more annotations. But also back to this question, regarding inter-annotator agreement, I think because people really agree on ethnicity and gender, it's like 0.8 kappa. So we get really accurate labels. The accuracy is good, is much better. But for subjective attributes like religion, for example, where the agreement is so low, the accuracies are lower. Yeah. Any more questions?
All right, so let's
Okay,
see
thank you.
again.